Okay, so now we have a couple more, rules and laws. We'll take a look at one that's kind of exciting, which is we just found, I like how it says recall, we just did it. It says if you have f plus g and you're taking the derivative, you can take the derivative of each piece. But the question is that true? But what about f times g and the derivative of that? And the question is it possible that that is simply the derivative of the first piece times the derivative of the second piece? So the derivative of f times the derivative of g. So we're going to take a look. Let's let f of x be x cubed and g of x be the square root of x, which is the same as x to the 1/2. If we were to multiply them together, we would get x cubed times x to the 1/2. And then understand that if I wanted to combine those, I would need to find a common denominator. And so I'd have to change x cubed into x to the something over 2. That's equivalent to x cubed. You can probably guess that that is a 6. So that's the same as x to the 6 over 2. So x to the 6 over 2 times x to the 1/2. Don't forget, in that case, we're going to add the exponents because we're multiplying things with the same base. So we'll have x to the 7/2. There we go. It's just some fraction work there. And then let's find the derivative of that using the power rule. If you want to pause, you can try it. So we have 7/2 x to the, and then we're going to subtract 1. But in this case, subtracting 1 means subtracting 2 over 2. So 7/2 minus 2 over 2. So understand that that is, of course, because that is equivalent to 1, but with the common denominator. So 7/2 x to the 5/2. So that's the derivative of f times g of x. Okay, so derivative. Now let's do it in pieces. So let's see if this thing is true here. Can we take the derivative of each piece, multiply them together, and get the same thing? So we take the derivative of x cubed. We take the derivative of our g of x. Okay, so that's just following our power rule. And then what happens when we multiply those two things together? 3 times x squared times 1/2 times x to the negative 1/2. So notice we get 3 over 2, so 3 times 1/2, and we get x to the, squared, x squared times x to the negative 1/2. Adding those exponents together would give us a 4 over 2 plus a negative 1/2. So that's going to be 3 over 2. So the key thing is, are these two things the same? Are they the same? And what we find, of course, is they are not. They are not. So you can't just say, oh, I have two things multiplied together. I'm going to take the derivative of one. I'm going to take the derivative of the other. I'm just going to multiply them together. Sorry, that's not going to work. So what we need to do is use the product rule. The reason that this works out so well is because you just have two, x to a power. So you can do it both ways. But a lot of the times you'll have maybe a polynomial times a trig function. In future stuff, you'll see, a polynomial possibly times an exponential, or an exponential times a trig, or a logarithmic function times a trig, or a polynomial, or whatever. So you have all sorts of combinations. And so in those cases, you'll really see that you can't just take the derivative of each thing, multiply them together. So here is the product rule. The product rule says that if you have two things multiplied together and you take the derivative, you are going to take the first function, multiply it by the derivative of the second function, and then add the the second function times the derivative of the first function. And that's everything that you have to do in order to get your derivative. So I'll show you an example. Okay, so here is the two functions, f of x and g of x that we saw before. But now we're going to use the product rule. So if we want to find f times g prime of x, what the product rule says is take the first function, multiply it by the derivative of the second function. We already know what these are. We've already done these. And then add the second function times the derivative of the first function. Again, I'm just taking these values from what we have previous in our notes. So in this case, you're going to see 1/2 x to the 6/2 plus -1/2. And so that's going to be 5/2 plus, as you can see, 3 to the 4/2 plus 1/2 on the x as the exponent on the x. So it's going to be another 5/2. So what you should notice is that this is 3.5 or 7/2 x to the 5/2, which is what we got the first thing that we did when we were starting this piece. This is a lot of work. I would not recommend it. In this case, for these two functions, I would multiply them together first and then just use the power rule. But again, sometimes you will have functions where the product rule is the only way to do it. This is just to show you that you can't just multiply each piece separately and then multiply them together. So the proof of this, let's do that and then, go from there. But the proof of this, all right. Whew, I have to literally look at my notes because it is a little bit involved, but it uses a very common math trick that you may see in the future, so it's good to know. So I've already have it set up here for you. I want you to understand I already have it set up. It's basically just saying use the limit definition. So notice I have the limit definition here. I have f of x plus h, g of x plus h, minus f of x, g of x over h. So it's just using the limit definition of the derivative. And we're just replacing x with x plus h in the first part, second part is normal. So the whole function here is f times g. That is the function that we're looking at. So what I'm going to write first is f of x plus h times g of x plus h. And then I'm going to draw a big line. And then over here, I'm going to put that f of x times g of x. So of course that should tell you, something's going in the middle. You can tell something's going in the middle. So here's a very common math trick. We need something else. I mean, we're still trying to get rid of this h in the denominator, so it's like, how are we going to do that? This is a very common math trick that happens in a lot of proofs. What we're going to do is we're going to add and subtract the same piece of something so that we're essentially adding 0. That is a very common math manipulation to help you move forward in something. So I would not expect students to ever know this, but we're going to subtract f of x plus h times g of x plus f of x plus h times g of x. So I want you to notice I just subtracted something and I added it, and they were the same exact thing. So I did not change what is in my limit. I just added 0 to it. And then in my denominator, I have h. And then what we're going to do, because this is going to take us somewhere, I promise, what we're going to do is I'm going to separate these. So I'm going to take my f of x plus h that I have right here, and I'm going to factor it from those first two pieces, So I have, what I have left is g of x plus h minus g of x. Again, I'm factoring it from the first two pieces. And then I'm just going to have that over h. And then, because the numerator is just adding and subtracting, from the second two pieces, I can now separate them. Again, because it's all just addition and subtraction. I'm going to factor out the g of x from the second two terms. See what I have left. So notice I'll have f of x plus h. All I'm doing here is algebra right now. I'm just doing algebra, but I have this all over h. Okay, so key to this is that the reason that this helps us, I'm just seeing where I want to go from here. I think I'm actually kind of doing okay, but I'll write one more line so that we have what we need, just to kind of show you. So the idea here is I'm going to have f of x plus h kind of here. And then I'm going to have this g of x plus h minus g of x over h. So all I did here was just kind of like move out f of x plus h. And then we'll have g of x. And of course, it's this whole thing, right? It's this whole thing. Again, it's this whole thing. So we have g of x, and then you know, kind of take out that other piece. F of x plus h minus f of x over h, like this, like this. So I didn't really do a whole lot there. I just pulled out that g of x and I pulled out that f of x plus h. But now, when we take our limit, you might be thinking, can we take our limit? We can, even though we have h in the denominator, because what we have here are just definitions of derivatives. And so instead of, you know what, I'm just gonna take my limit now. I'm ready. I'm gonna take that limit. So now we can take that limit and see what we're left with. So try to follow along. So when I take the limit of this first piece right here, when I take the limit as h goes to 0 of f of x plus h, all that happens is h goes to 0 and I'm left with f of x. When I take the limit of the second piece of the first piece right here, notice that is just the derivative of function g using the limit definition. So when I take the limit as h goes to 0 of that thing, I just get g prime of x. When I take the limit as h goes to 0 g of x, it doesn't even have an h. So it's just g of x. And then when we take the derivative of this other piece, take a look at it. When we take the limit as h goes to 0 of that other piece, notice all that is just the limit definition of the derivative. So we get f prime of x. And what we have here is the product rule. We have just proven it. So now we can use it. Yay. All right, I'm going to do one more thing and then take a break. So at the top here, suppose f is a differentiable function. We have, find the derivative of f of x squared. F of x quantity squared. So we're going to use the product rule to find it because that's what we have so far. So it's f times f, and we're taking the derivative. So we're just going to use the product rule, and you'll get the product rule down. So it is the first function times the derivative of the second function plus the second function times the derivative of the first function. But everything's just f. So I want you to see that these are like terms. They are the same exact thing. F times f prime, f times f prime. So now we just get 2f times f prime. So all this is all f's, but that's our answer. So it's the same as just saying 2 times your function times the derivative of your function would be the answer. And what you should know, or not know, sorry, what you should know, or like what you will know in the future, is that there's an easier way to do this, and it's called the chain rule, and that's something that we'll learn soon. But this is another way to think about it, is using the product rule just on the same function. Totally valid, and it's something you can do. And then we have consider f of x divided by g of x. And the question is, if you take those functions and divide them, what is the derivative of that? So we're going to go back to the functions that we were working with earlier here. And we've got our x cubed and we've got our square root of x. And let's do it two ways, see if they're the same. So first thing we're going to do is we're going to take our f of x and we're going to divide by g of x. So that just means this. Then we want to go back to those fractional exponents. We have x to the 6th over 2 divided by x to the 1/2. So you want to remember in this case, when you divide two things with the same base, you're going to subtract their exponents to get x to the 5/2. And then we take the derivative of that. We can just use the power rule. We have x to the n. So 5/2 x to the 5/2 minus 1, which is 2 over 2. So x to the 3/2. Now let's do it the other way. So now let's take the derivative of the numerator. We already know all this stuff, 3x squared. Take the derivative of the denominator. We already know this. Looks like this here. And then we're just going to simplify that so we can see if they're the same. So what's going to happen is 3 divided by 1/2 is 6, because 3 times 2. And then when you have those denominators, the exponents there, we're still going to subtract them. So we're going to have 2, which is 4 over 2 as a fraction. 4 over 2 minus a negative 1/2. So we're actually going to add those together and we're going to get 6 to the 5, x to the 5/2. And then when we take the derivative of this, oh no, we have the derivative. This is it. This is our answer because we took the derivative of the numerator and denominator and we divided them. So notice these two things are not the same. They are not the same. No. So of course, what this tells us is one of these things is wrong. And I'll tell you, this is the one that's right because we just rewrote it and then used the power rule. And that's a legit way to do it. So this is the way here that is wrong. So if you are taking two functions and you're dividing them, you cannot just take the derivative of each piece. If you need to find the derivative of them, you can't just take the derivative of each piece and divide. So here is what we have to do. So here's what's called the quotient rule. Quotient because we're talking about division. So love it or hate it, we've got this division sign here. So when you have a function over another function and you're taking their derivative, you're going to take the bottom function, multiply it by the derivative of the top, and then you're going to subtract the top times the derivative of the bottom. That's kind of how I say it there because it doesn't matter if they're f or g or b or t or s or p or whatever, and then divided by the bottom squared. So this is the quotient rule, and you can find a proof for this. We are not going to do it, but there is a proof. You can actually do a proof based on the product rule as one way to do it, but there is a proof and it tells us that it works. So it's a lot of pieces. So we're going to take a look. So notice it can get a little bit confusing. This function is called g of x and we're finding its derivative. However, really just focus on the fact that we have the top and we have the bottom. And that's really how you want to see this because it is technically two functions. Your numerator is 2x plus 3. Your denominator is x plus 1. What we learned is you can't just, this is the whole point, you can't just take the derivative of the top and say, oh, derivative of the numerator is 2. Oh, derivative of the denominator is 1. Done. Okay, that's not how it works. So you have to use your quotient rule in a case like this. So what we do is just following what we have there, just thinking of top and bottom. That's all we have to think about. It's actually probably more straightforward than you think. So we take g of x. In this case, g of x is just, think of it, just it's your denominator. So we take the denominator. We're going to multiply that by the derivative of the numerator. The derivative of the numerator, 2x plus 3, is just 2. Again, I'm using the power rule. I'm using the derivative of x here. Just basic stuff. Then I subtract from that the numerator, 2x plus 3, what I have in the top, times the derivative of the denominator, derivative of x plus 1, well, derivative of 1 is 0, derivative of x is 1, and then over the denominator squared. That g of x squared, denominator squared, no derivative there. And then it is possible to simplify a little bit. We have 2x plus 2, just depends on whether we're asked to do that or not, minus 2x minus 3 all over x plus 1 squared. So often little simplification you can do there. The 2x's simplify and we just get a negative 1 over x plus 1 squared. But obviously you can see that that's a very big difference from just taking the derivative of the numerator over the derivative of the denominator. Very, very big difference. But the quotient rule is needed in a case like this.